Welcome to Physics 371 Online. I'd like to give a brief overview of the content from section 1.2 in the textbook dealing with vector differential calculus. And to start, we'll go back to the simple properties of a one-dimensional function f of x that you're familiar with. We can write a small change in the functional value f in terms of a small change in the variable x, and in so doing we involve this quantity df dx that we call the derivative of f of x. Geometrically, what it represents is the slope of the function. For a three-dimensional function, we can write something very similar, imagining that we have a function t of x, y, and z. We can write a small change in t in terms of a small change in x, y, and z. And what this means spatially is, if you move from one point in space to another point through a very small displacement along x, y, and z, the functional value of t will change. So in this expression, we introduce in parentheses terms that are called partial derivatives of t with respect to the coordinates. It's useful to take this quantity dt and rewrite it as a dot product that involves a differential displacement vector dl. How do we do that? Well, we go back to the expression for dt, and we realize we can form a dot product between this differential displacement vector on the right and a vector on the left that has as its components these partial derivatives. And we give a special symbolic name for this function, this vector on the left-hand side. We call it the gradient of the scalar function t, or del t. And if we use that symbol, then we can write a change in the function t as the dot product of del t, or the gradient of t, and dl. The reason that we put the arrow over the del, the inverted triangle, is because t itself is a scalar function, but this gradient of t is a vector function. But what does it mean? It must be some kind of a derivative. But what kind of a derivative? And it's a little more complicated than the one-dimensional function, because in 3D the slope is different along different directions. So what we can see is that this gradient del t is the slope of t along the direction in which it's the largest. Or we can say that the gradient of t, or del t, is the magnitude and direction of the maximum slope of t. So even though we define this del t as a single symbol, we can unpack it and regard it as the result of a differential operator del acting on the function t. And this del we call the del operator, or just del for short. We can define it in order to make sense of this expression, the gradient of t. We define the del operator as a vector whose components are derivatives with respect to x. Note that this by itself does not really have well-defined magnitudes unless it operates on a specific function, because then the derivatives acquire specific values and it becomes a real vector. So although del is not really a vector in the strictest sense, we still use vector notation, because when it acts on a function, it produces a vector. Now t was a scalar function. And if you're thinking about an example, imagine a room which at each point in the room has a different temperature. So give me an x, y, and z, and at that point x, y, and z there's a temperature for the air in the room. But in physics we often use vector functions to describe quantities that have not only a magnitude at different points in space, but also a direction. So let's imagine such a function and call it v of x, y, and z. So for an example, using the room analogy, this could be the velocity of the air in the room at different points, which has not only a magnitude or a speed, but also a direction. The del operator, being a vector operator, can act upon this vector v in two ways, either through a dot product or through a cross product. So del dot v, if you actually work out the expression using the definition of the del operator, it gives this result here. Note that it's a scalar, and we call this the divergence of v. We can also make the cross product of del and v, del cross v, which has the standard representation as the determinant of a 3 by 3 matrix, and for notational purposes we call this the curl of V. Now what do these things mean geometrically? Oh, and by the way, it would be good practice to work out the expression for the curl using this determinant notation. What do they mean physically? Well, geometrically, the divergence, or del dot V, is large at a point in space that V spreads out or diverges from. So at the point indicated by the dot here, if V points outward and away from that point in all directions of space, then we say at that point V has a large divergence. By contrast, del cross V is large at a point in space that the vector function V circulates around or curls around. And so if V makes loops around a point in space, indicated here in the sketch, at that point we would say that V has a large curl. Well, we'll finish off this section of the text just by surveying quickly a couple of rules similar to the product rule for the derivative of the product of two functions. Things are a little bit richer when we use three-dimensional functions because the del operator is our differential operator, and we can apply the del operator in various ways to products that involve scalar or vector functions. So let's just quickly take a look. We can form two of these with the gradient because we can take the gradient of the product of two scalar functions, or we can take the gradient of the dot product of two vector functions. Both terms inside the parentheses are scalars. We can also take the divergence of two different kinds of products. We can take the divergence of the product of a scalar and a vector function, or we can take the divergence of the cross product of two vector functions. And similarly, we can make two more products involving the curl of products of vector and scalar functions. So FA being a vector, we can form the curl of that, and A cross B being a vector, we can also form the curl of that. And these kinds of expressions occur frequently enough that the rules, the results for each of these 6 expressions are recorded in the inside front cover of your textbook, and you'll actually be assigned several of these to evaluate for homework. So finally, since in physics you know that second derivatives of various kinds of quantities often have physical significance, let's review what kind of second derivatives arise from the del operator. First, we can take the divergence of a gradient, right? The divergence of the gradient of t, which is given by this expression here, and we actually define a special way of writing this down, del squared of t, because it involves these second derivatives of t with respect to x, y, and z. And we also call this the Laplacian of t, named after the famous French mathematician. We can also take the curl of a gradient, because a gradient is a vector, so we can take the curl of that. Remarkably, it turns out that no matter what the function of t happens to be, the curl of the gradient of t will always be 0. We can also take the gradient of the divergence of a vector function, and although it's possible to do this, and you can work out the expression for it, it just doesn't occur very often in physical applications, so we won't consider it any further. We can make the divergence of the curl. This is a little bit more interesting, but just like we saw in number 2, this has the special property that no matter what the function v happens to be, the divergence of the curl of v will always give 0. Maybe this makes sense if you think about it, because the curl measures the circulation of the function, while the divergence is a measure of how it spreads out in space. So perhaps it makes sense that a function with a large curl would have a 0 divergence, and vice versa. Finally, we can make the curl of a vector function, and when you evaluate the left-hand side and simplify it, you get 2 terms. But even though it looks kind of complicated, there's really nothing new here. The first term on the right is simply number 3, which we said usually doesn't have any physical applications. The second term on the right is a very simple variation on number 1, where the Laplacian is of a vector function. instead of a scalar function. So these second derivative expressions are also recorded in the inside cover of your textbook for reference in future situations. So that pretty much wraps up section 1.2. Hope this was helpful, and I will see you in class.